Okay, so a square root, pretty much everybody, we've seen square roots before, and I know that print is kind of small there. Let me hopefully make that a little bigger. Okay, what we know is that if the number c is a square root of a, if c squared equals a. So, for example, 3 is a square root of 9 because 3 squared equals 9. Okay. Similarly, though, negative 3 is a square root of 9 because negative 3 squared is equal to 9. But if you have a calculator near you and you take the square root of 16, what does it say? It just says 4, right? It doesn't say plus 4 or minus 4. When you see just the square root, so you just see the square root of a number, this is what we call the principal square root, or it's the non-negative square root. Okay? If you're going to take the negative square root, it will actually have a negative sign out front. But anytime you take just, quote, the square root of a number, you're looking for the principal square root or the non-negative answer. Okay? Now, we've talked about domains of functions earlier in the semester, like when we have fractional functions, we have to leave out whatever makes the denominator 0. When you're talking about square root functions, you have to make sure that what's underneath the radical is bigger than or equal to 0. Because when you take the square root of a negative number, we don't get a real number as our answer. We get what we call an imaginary number, which we'll talk about a bit later. But for any time you have a square root function, if you want to find the domain, what we're looking for are the legal values of x. What can I plug in for x and get a real answer out of this function? And that domain will be the set of x's that make what's underneath the radical bigger than or equal to 0. Okay? So we also have to review, how do we solve this inequality? Well, remember, when you're solving a single variable inequality, we do it very similar to what we do with equations. We want to get the x alone on one side of the inequality and solve. One thing you have to be careful about is if you multiply or divide by a negative number, what do you have to do with the inequality symbols? Almost, we flip it. And we'll do one of those here in just a minute. In this case, we're just solving 3x is bigger than or equal to 15. So we're just going to divide both sides by 3 and get x is bigger than or equal to 5. So our domain would be the set of all x such that x is bigger than or equal to 5. So that would be the answer in set builder notation, or if we wanted to put it in interval notation, we need the numbers that are bigger than or equal to 5. So I'm going to start at 5. Remember, this is the bigger than or equal to. Oh, sorry. And we're going to go out to positive infinity. Okay. The square brackets are from the equals sign. If that had been strictly greater than, it would have been parentheses here. Okay, so to find the domain of a square root function, you want to take what's underneath the radical and find where that's greater than or equal to 0. So why don't you guys try this one? And when you start getting answers, if you wouldn't mind saying done or okay in the chat so I'll know when we can start. And it's okay if you aren't finished with it yet, but okay. That's the square root of 2x plus 5. Awesome. Okay, so we're starting to get some answers. What do we do to find the domain here? We take what's underneath the radical and solve for where that's greater than or equal to 0. Subtract 5 from both sides, we would get 2x is bigger than or equal to negative 5. Divide both sides by 2. And we would get x is bigger than or equal to negative 5 halves. Now, it's okay that I got a negative number over here. I didn't flip the inequality because the number I divided by was a positive 2. You only flip the inequality when you multiply or divide by a negative number. So you could put it in set builder notation as the domain is the set of all x, such that x is bigger than or equal to negative 5 halves. Or in interval notation, we would start at negative 5 halves and go to positive infinity. So depending on how they ask you to leave your answer, sometimes they'll ask for domains in terms of set builder notation. Sometimes they may ask for domains in terms of interval notation. And as we move forward into other topics, we will be using interval notation more and more. So in this case, I would for sure try to practice with using the interval notation. It looks like in this section they ask you for interval notation sometimes. All right, so what about graphing one of these functions? Well, if you don't do what? Oh, okay. So if you don't know what a graph looks like, what do we usually do other than grab our graphing calculator? I know we do that a lot. But if we really don't know what the shape of a graph looks like, we typically plot some points, right? So if we want to plot some points here, the first thing I would do is try to figure out what the domain of my function is so that I choose to plug in appropriate x values. So for my domain here, I would take x minus 3 is bigger than or equal to 0. So that would be when x is bigger than or equal to 3. So there's no sense in me trying to plug in x values like 1 or 0 or negative 1 because they're not in the domain of my function. So I am going to plot some points after I find both coordinates by doing, by doing a t-chart. So I'm going to pick some x values that are bigger than or equal to 3, and I'm going to plug them into my function values. So I'm personally going to start with 3, and then I'm going to plug in 4. And how about 7? And we'll talk about just a second why I picked 7 instead of, say, 5. All right, if we plug in 3 here, this would be the square root of 3 minus 3, which is the square root of 0, or 0. So 1 point on my graph will be the point 3, 0. When I plug in x equals 4, I will have the square root of 4 minus 3, which is the square root of 1, which is 1. and I have the point 4, 1. If I replace x with 7, I will have the square root of 7 minus 3, which is the square root of 4, and that is good. So we have the point 7, 2 as well. So if I plot those points, I would have 3, 0, 4, 1, 7 would be about here, and 7 would correspond to a y value of 2. So I'm going to start at 3 and go to the right, connecting with a smooth curve. This graph paper is not really big enough there. And we would get a graph that looks similar to that. Now, why do you think I chose 7 instead of, say, 5? Right, it wouldn't be a, quote, nice number. I picked 7 because I knew I would get 4 under there. Now, it's perfectly fine if you did pick 5 or, say, 6. If you chose 6, you would have the square root of 6 minus 3, which is the square root of 3. The problem is graphing that exactly, as far as that point exactly, is a little bit difficult because that's an irrational number. It's a non-repeating decimal. So I tried to pick a number where I would have a perfect square left underneath the radical is all. Any questions about that graph? All right. So what about this one? This one's a little bit different because now the 2 is outside the square root. All right? So the domain, remember, we only deal with what's inside the radical unless we had like a fraction out here or something like that. We want to make sure that to be in the domain that what's underneath the radical is bigger than or equal to 0. Well, what's nice about that one is I didn't even have to do any solving. Since it's just an x, the domain there would be x is bigger than or equal to 0. Since this part is just a 2, it doesn't restrict the domain at all. It doesn't matter what x is. This part is just 2. So the domain would start at 0. So if I was going to plot some points, I would start with 0, and my y values would be 2 plus the square root of x. Now, since x is exactly what's underneath the radical, I would probably just pick x values that are perfect squares. Remember, your perfect squares are things like 1, 4, 9, 16, 25, that kind of stuff. All right, so if I plug in 0, what would I get for the y value over here? 2, exactly, because it would be 2 plus the square root of 0, which is 0, or 2. If I plug in 1, I will have 2 plus the square root of 1, which is exactly. If I plug in 4, I'll have 2 plus the square root of 4. And last, 2 plus the square root of 9 would be 5. So I'm going to plot the point 0, 2, 1, 3, 4, 4, and 9, 5. Okay, and then just connect the dots. Okay. Now notice the shape here is fairly similar to the shape here, and that's common for your square root functions with just a linear term underneath. Now sometimes they may be flipped going the other direction depending on what the domain is, but the shapes will be similar. Any questions? Yes, and some of them, you know, depending on what's underneath here, sometimes they can get steeper or flatter. You know, you could have one doing a much steeper curve. You could also have one going this way. Oh, sorry, not that y'all can see that. You could have a graph of a square root function going this way if you took the negative of it, or depending on what's underneath the radical, it could also point this way. But notice that the curvatures are very similar even though. All right, so let's look. Okay, I don't remember who it was that asked, but let's look at an application of one of these problems. Now, I know a lot of times the applications right now are a little bit, you know, they seem a little artificial. They're trying to give us ones that might, you know, be pretty straightforward to solve, because honestly, a lot goes into finding a formula for application problems. So on this one, it says the attendants at a parking lot park cars in temporary spaces before the cars are taken to long-term parking stalls. The number n of such spaces needed is approximated by the function n of a is equal to 2.5 times the square root of a. Now, and that's where A is the average number of arrivals in peak hours. So like maybe we get a whole lot more arrivals at 8 a.m. than we do at 2 p.m. or something like that. We want to find the number of spaces needed when the average number of arrivals is either 64 or 69. So we're going to plug in nothing more than A equals 64 on the first part. So that would be 2.5 times the square root of 64, or 2.5 times 8, which is what, 20? All right. And then we also want to find the number of parking stalls we need for arrivals of 69. So we're going to plug in 69, and we will have 2.5 times the square root of 69, which is I'm getting 20.7665. And in the instruction on this one, it says round to the nearest integer as needed. So if we round this up to the nearest integer, because think about it, can we have 20.7 parking stalls in use? Well, you know, I guess depending on how people park, you might could, but not really. You need a parking stall for everybody. So we're going to round that up to 21. Okay. Any questions? All righty. Now, you guys do know that these notes are in Canvas that you can always print off or write down or anything you want to off of them before class, right? If you go to modules, I try to post these. If I have notes that I'm going to write on, I try to post them at least the day before. So those are always available to you. All right. So, yes, sir. That last question? Okay. All right. So we have in this chapter, we really just do a couple of sections. We do section 6.1 and 6.6. So section 6.1 that we just talked about was radical functions, kind of to go along with the radical equations to go along with the rational equations that we did on Monday. Whereas 6.8 is something that's fairly different from those. What we're going to talk about in 6.8 is when functions are increasing, decreasing, or constant. So let's just hide that for a second. Just in general, if I ask you what it means to you if I say something is increasing, can anybody think of a word or two that might describe what you mean when you say something's increasing? I'm sorry, what? Growing, absolutely. Is it getting bigger or smaller? Bigger. That's exactly what it means mathematically too. If we say something is decreasing, it's getting smaller. And if it's constant, it's not changing. Exactly, it's staying the same. Good. Now, I say that before I let you look at this definition, because when we look at the definitions of increasing, decreasing, and constant, it can be a little scary. When you are talking about mathematically, it says a function is going to be increasing on an open interval if for all a and b in that interval, a is less than b implies that f of a is less than f of b. That's just a mathematically precise way to say that if your function is increasing, your graph is going up to the right. Now we do read our graphs from left to right. So when it's going to be increasing, it will be getting bigger as you go from left to right. Decreasing, if a is less than b, implies that f of a is greater than f of b, so that means going down to the right. It's constant on an interval if it's just flat. Okay. Now, if you're given a graph and asked where it is increasing, decreasing, and constant, what we're going to do is we're going to start from left and start moving to the right. Okay? So if I look at this point, and this point, those are the points where the graph seems to change directions. So let's start from the left and go to the right. On that part of my graph that I'm showing right there, is it increasing, decreasing, or constant? Now remember, we're going from left to right, we're going down to the right. Exactly. I know when we just glance at it, it goes, oh, it looks like it's going up to infinity. And the y values are going up to infinity. What would be nice is if we drew the arrow going down, but that's where they're coming from, is positive infinity. So this part, they are decreasing. Okay. What about between this point and this point? It is constant. Good. From here to here, increasing, and from here forevermore, we're going down. So it's decreasing. Good. So we would say that if you're going from, say, 3 to 5, we would be increasing. Now these are x intervals. So be careful, because that looks a whole lot like a point, doesn't it? So it all depends on the context. Here we were asked to determine the intervals where a function is increasing, decreasing, and constant. So it was increasing between x's 3 and 5. It was decreasing, okay, from here all the way to the left. How far does that graph go to the left? Well, based on that arrow, it goes forever to the left. So the interval there would start from negative infinity up to the x value there would be -1. And it was also decreasing over here, which starts at x equals 5 and goes forever to the right. So that would be 5 to positive infinity. Now, be careful here, because a lot of times people say, but it's going to negative infinity. Why would I put a positive infinity there? Remember, here the y values are going to negative infinity, but as you get further and further to the right of your graph, the x values are going to positive infinity, and these are x intervals. So we're increasing from 3 to 5. We're decreasing between negative infinity and -1, and 5 and positive infinity. And then we are constant on this graph between, what was it, -1 and -3. Or pardon me, -1 and +3. Yeah. Okay? Any questions about that? All right. So let's do one more and then I'll let you guys try one on your own. So we're looking at this example 1 over here. Okay. Now notice this particular graph actually stops at the point 4, 3. So we won't be going to positive infinity on the right because of the fact that we don't have an arrow over there. It just stops, right? So think about it for just a second and then we will go over it, or if you want to, if you are wanting to copy it down, that's perfectly fine too. So I'm going to give you a couple seconds to look at that. All right. So we're going to look at the intervals where the graph is going up to the right are going to be the intervals where we're increasing. So that would be here and here. What are the x values in those intervals? Well, with this arrow, oh, go ahead, I'm sorry. Perfect. And what about this one? 2 to 4, good, excellent. Okay, decreasing, is this one ever decreasing? Between, perfect. And then it is constant between -3 and, you got it. Awesome job. Okay. What you have to remember is that we always go from left to right. So if you look at this graph from left to right, the graph is going up to the right. Yeah, and that's the hardest part of these, I think, is remembering that we're always looking at, is it going from left to right? Is it going up to the right, or is it going down to the right? Okay. I know, but that's an excellent question. But remember that arrow just indicates that this graph continues in that direction forever. Yeah. All right, so you guys try this one. I'm going to give you a couple minutes and then we'll compare our answers. All right, are we ready to look? All right, so increasing, this one would be from -2 to +2. Decreasing, perfect. Constant, that's it. 2 forevermore. Good job. Anybody have any questions about either one of those? This one? or the, okay. Oh, you mean like over here? Because this graph has a little closed circle there, so it stops at that point. And so it doesn't extend forever in that direction. The same way this one stops at -5 and doesn't keep going. And you tell that because it doesn't have an arrow there. Like if it just stopped right there, that would, instead of going to negative infinity, it would have been from -5 to -3. Okay. It's kind of, yeah, you've got to pay really close attention to when it's an arrow versus a dot. I'm going to have to get a different desk that doesn't shake every time I erase. Okay. So when you have those points where your graph turns and changes from being increasing to decreasing, the turning points are what we call relative maximum or relative minimum values. So once again, the definition may look a little bit scary when you look at it, but when you have a relative maximum, it just means that if there's an open interval such that it's the biggest point in that interval, in other words, basically it's going to be a mountaintop on your graph. It's going to be a peak on your graph. And a relative minimum is a point where your graph changes from decreasing on one side to increasing on the other. So it's a lowest point close to it. In other words, these are turning points. Okay? Now, it doesn't mean that it has to be the absolute biggest point on your graph or the absolute smallest point on your graph. It's just a turning point. Some graphs have no absolute biggest or smallest. If you have a point where it's the absolute biggest point on your graph, instead of calling it a relative maximum or minimum, we call it an absolute maximum or minimum. But right now we're just looking for turning points. So if you look at a picture like this, and this is where your graphing calculator really will come in handy, but most of these they graph for you. But if you want to find a relative maximum or a relative minimum, you're looking for the points where you're turning. So if you just look at that graph just close to this point, is that a peak on your graph or is it a valley? It's a valley. It's a low point, right? If we poured water down there, it would be collecting at that point. So we would have a relative minimum of -1.282 at x equals -1.764. Now, why did I write it that way? I wrote it this way to emphasize the fact that when you're asked for relative extrema, the y value of the high points and the low points are actually the maximum or minimum values. Okay, now sometimes they'll ask you to put the answer in point form. Sometimes they'll ask you for what the maximum value is. A lot of times they'll say we have a relative maximum at x equals blank and it is a value of blank. So instead of putting it in point form, they separate the x and the y. This one has that low point here. It has a high point turning point here. So at x equals -0.236, we have a maximum, or a relative maximum, of 2.282. The y value is the maximum value. The x value just tells you where it occurs. Okay, what are they? They're the turning points of your graph, where you go from increasing to decreasing or decreasing to increasing. So this graph would have a relative minimum at x equals 0.167, and the minimum value is 0.870. It's the y value that goes with that x when they identify it. What about a relative maximum there? Do we have one on this graph? Excuse me. We do. And the relative maximum would be at x equals negative 1.500 with a value of 5.500. Is everybody okay with that? We really are. If you plug that into your graphing calculator, you could find those points, but they identify them for us right here. And so we didn't really have to even graph it. They graphed it for us. Now, a couple things. To actually find those points by hand requires calculus. And so that's why they're actually identifying the points on the graph, is because it's beyond what we're ready to do algebraically or with calculus. All right. So let's look at an example of a word problem or an application of some of this stuff we've been doing. So this says that a dentist has 24 feet of dividers with which to set off a rectangular area for a play space in her waiting room. If a corner of the waiting room is used for the play space, the partition needs to form only two sides of the rectangle. So in other words, we've got a room. Here's our waiting room, and we're going to form a play space just in the corner of that waiting room. So our play area is going to be just there. So the two sides of that play area are formed by the walls of the room. Now, we have 24 feet of dividers. Excuse me. All right. Now, we want to express the floor area of the play space as a function of the length of the partition, find the domain of the function, and using the graph shown below, determine the dimensions that maximize the floor area. So what we have is this side plus this side has to be equal to the amount of dividers that we have, which is just 24 feet. So if I let this side be x feet, then this side would have to be 24 minus x feet. Because if I already used 10 feet on one side, I would only have 14 feet left to use on the other side. So if x is the length here, then 24 minus x would be the width. And how do you find the area of a rectangle? You take the length times the width. So our area function would be x times 24 minus x. Or if we simplify that, that would be 24x minus x squared. Okay? Is everybody okay so far? Okay, now they graphed this function for us right here. Okay, you could definitely go into your graphing calculator and plug it in there, but they're going to give us the graph already. Now, they want us to find the domain of the function. Okay, in general, if you were just looking at the graph of 24x minus x squared with no physical restrictions on it, the domain of that function would be all real numbers. But we're looking at a physical application where x is the length or the width, either way you want to call it, of the play area. So what can x not be less than? Why is that so shaky? it would have to be less than 24 for sure, because that's all the partition feet that we have. So we know that it's going to have to be less than 24. Good. And it's going to have to be bigger than 0, because we can't have a negative number of feet for our play area. So the restricted domain, or the domain that's relative to the application problem at hand, would just be between 0 and 24. Now, they also want us to use the graph that they showed to find the maximum floor area covered by this play space. Well, remember, the maximum is the peak on the graph. So our maximum is 144 at x equals 12. Because that's our relative maximum here. That represents the square feet of floor area, because that's what this function represented. So we would have a maximum of 144 at x equals 12. So that was the length. And the width of the play area was 24 minus x, which would be 24 minus 12, or also 12. So in other words, we have a maximum area here when we have a square play area. Questions? All right. If we have time to come back and look at one more word problem, we will. But I want to make sure that we have plenty of time to look at the one other different type of topic that we have, which is the idea of a piecewise defined function. And guys, I know that right now it's like they throw in 47 different kinds of topics in a single section. That will get less as far as that's concerned after we get out of this kind of introductory material, which is plenty challenging on its own, but they do throw in, I know, a lot of topics in a single section. As we get a little bit further, the topics will flow a little bit better from one into the other. Okay. So the last thing that we're going to talk about in section 6.8 is that of a piecewise defined function. How many of you pay a phone bill or an electric bill or a water bill? Pretty much all of us, right? Okay, so you actually deal with piecewise defined functions every month when you pay your water bill, your phone bill, your electric bill. How is that possible? Well, for example, summertime, they charge a different amount for your electricity up to, well, and they do in the wintertime too, but they'll typically charge you a certain amount of money per kilowatt hour up to a certain usage. And then once you pass, if you use more than that, they're going to charge you a different amount for the remaining kilowatt hours. So it's one function for some x values, it's a different function for other x values. Same thing with water bills, and same thing with phone bills sometimes. Now, most of us, for phone bills anymore, most people have unlimited whatever for a flat fee. So that's not as much the case with phone bills anymore, but very often with other sorts of, electric or water, that kind of thing. So what a piecewise defined function is just as the name suggests, it's a function that's defined in pieces. So it's defined one way for some x values. It's defined other ways for other x values. So if you're going to evaluate a piecewise defined function at a particular x, what you have to do is decide which piece is in play. So if you wanted to find for this function, you wanted to find g of negative 2, you would have to ask yourself, for this x value negative 2, which of these intervals is it in? Is negative 2 less than or equal to negative 1? Is it between -1 and 3, or is it bigger than 3? Well, -2 is actually less than or equal to -1. So for g of -2, we would use the top function. So g of -2 would be -2 squared minus 1. And what do you get when you square that out and subtract 1? 3. Perfect. Because remember, this is the -2 times -2. So that would be +4. Okay. What about g of 1? Is that in this first interval, the second interval, or the third interval? Where is x equals 1? It's in the second one. Good. So we would use that second formula to evaluate g of 1. Since it's just -x, it would just be -1. And then g of 3, is it in the second or the third? It's also in the second, because remember that says for x is less than or equal to 3. We actually have 3, so we would use the second formula. And then last, we have g of 4. 4 is in the third interval for x's, so we would use the third formula. So g of 4 here would be just 6. Because the formula is g of x equals -x, and so when you replace x with 1 or 3, you get either -1 or -3. You bet. Now, if you want to graph a piecewise function, do it in pieces. Okay? So don't stress about, there could be 2 or 3 bits of this function. Don't stress about it. Let's just go one piece at the time. So what we're going to do is we're going to graph g of x equals 2x. Oh, I'm sorry. Oh, okay. G of 4, since 4 is in the interval that is bigger than 3, we use the third function, and since it's just a constant 6, we didn't have to plug it in at all. All right. Is everybody good? Okay, so we've got g of x equals 2x for x's less than -1. So I'm going to just graph this function, but I'm only going to graph it up to the point where x is -1. What kind of graph is that? That is a, what did we do last week? What kind of graphs? It's a line, exactly. So I should have gone 2 weeks ago. We were doing inequalities last week, weren't we? But it is indeed a line. So what's the slope of that line? It is 2. Perfect. And if I asked you what the y-coordinate of the y-intercept is, I know it's a little quick review, isn't it? It would be 0. Very nice. Now, we're just going to plot a couple points. Okay, so I'm going to go with x equals, say, -2 and -1. Why didn't I pick 0? Well, this graph is only good for x's that are less than -1. So technically the point where x equals -1 is not going to be a point on this line, but that's the point where it stops. So I want to know what this graph would look like. Where is my stopping point? So if I plug in x equals -2, I get -4. And if I plug in x equals -1, I get -2. So this graph would be the line connecting these 2 points but I am going to draw an open circle at this point because it was strictly less than. If that had been less than or equal to -1, I would have drawn a closed circle there. That's the stopping point for this part of my graph. Now these were x is less than -1, so it'll continue to go in that direction to the left. Okay. Now once again, why do I have an open circle there? It's because this was for x is strictly less than -1. So at the point where x actually equals -1, I have to indicate with an open circle that that point is not included. Now we're going to do the same thing for this part of our graph. So for part 2, we have g of x is equal to x minus 3. And this is true for x's bigger than or equal to -1. Now, what's the slope of that line? 1, and what's the y-coordinate of the y-intercept? You rock. Good. Remember, the coefficient of the x term is the slope, and the constant is the y-coordinate of the y-intercept. Once again, just a little bit of a review. Now I'm going to plot some points. I want only x's that are bigger than or equal to -1. So I'm going to start with -1 and maybe do +1. We could have done 0, but all right. If I plug in -1, I will have -1 minus 3 is -4. And if I plug in +1, I will have 1 minus 3, which is -2. So I plot these 2 points. We have a point at -1, -4. And we have a point at 1, -2. Connect the dots with a line. Every time I say that, my line gets a little bit. Okay. Now notice, I have a closed circle at that end point right there. And that's because this graph was true for the x's that are bigger than or equal to -1. At this point, that was when x equals -1, so that point is on this piece of the graph. Questions? All right. We have about 5 minutes left, and so if you guys are up for it, I would like to try one more word problem from the applications section. So if we run out of time and you need to leave, you feel free to do so, and I'll make sure that, you know, when I post the video, you'd still be able to see this last example. Okay, so we have on this one that a blimp can be seen flying at an altitude of 7,100 feet above a motor speedway during a race. Okay, oddly specific there, isn't it? Okay, the slanted distance from the pagoda at the start line is d feet. Express the horizontal distance h as a function of d. Okay, guys, when you have right triangles, is there anything you know about the sides of a right triangle? There's a specific thing, and I'm trying to figure out a way to lead you into it. It's something theorem. Pythagorean, excellent, good. What the Pythagorean theorem tells us is that if you take the squares of the sides of a right triangle and add them together, you get the square of the hypotenuse. Now remember, the hypotenuse is always the longest side of a right triangle. It's the side that's opposite the right angle. So in this case, we would have h squared plus 7100 squared is equal to d squared. Now what we're looking for is we want to find h as a function of d. In other words, we want to solve this for h. So if I want to solve this for h, I would subtract the 7100 squared from both sides. And then I have an h squared. What undoes a squaring? What's the opposite of squaring something? Not quite in this case. I didn't ask that question very well, I'm sorry. But yeah, we would take the square root. Thank you for bailing me out there. I didn't ask the question very well. I apologize. All right, so if we want to undo a squaring, we're going to take the square root. Now, typically, if you solved that for h by taking the square root, we would have d squared minus 7100 squared with a plus or minus out front, because it could be plus the square root or it could be minus the square root. In this application, though, h has to be a positive number, right? And so we would have to go with the positive square root only. So this would express h as a function of this slanted distance d. And that's all they actually asked you to do in this problem. They didn't ask us to solve it at a particular time or anything like that. They're just getting us in the habit of relating variables in an application type setup. Okay? Any questions? All right. So for Monday, your homework is 6.1 and 6.8. I noticed that a few of you are a little bit behind. You hadn't opened like one or other of the new sections, but I also know that a lot of you work during the week based on your practice assignment in Gradescope. But I just encourage you to try to get caught up over the weekend if you can. If you get stuck on something, shoot me an email or go into Canvas and make an appointment for my office hours. I am most happy to meet with you during office hours. And there's also links to Tutoring Center. But let me know if you have questions, and I'd be happy to help you out. If only I could make you have 28 hours in the day, huh? Because I know a lot of times that's what happens is we run out of time. But I will talk to you guys on Monday, if not before. Have a great weekend.